All right, so today's physics video is about bow and shock waves. This one pretty much picks up where the last one left off. In the last video, we talked about what happens if your source was moving. And what we found was you get this crazy pattern where as the source moves, what's really happening, and I don't think I said this in the last video, but kind of what's happening is as your source moves this way, it's sort of chasing after the waves that it creates. But notice, everything we talked about in the last video, the source was still moving slower than the wave that it created, which is why the source, this little dot here in the middle, never got ahead of the circular waves that it was creating. Okay, it did get, though, if you go from slower to regular speed to faster, it got closer and closer to sort of catching up with those waves. All right, so now the next question is, what happens when the source catches up to the waves? What happens when the source is going as fast as or faster than the wave? All right, so what happens is you still get the Doppler effect. A little bit differently, it gets a little bit more complicated because your circles are overlapping. But more importantly, you get constructive interference. The waves are going to start to overlap once the source starts moving at least as fast as the wave, and it creates what are called shock waves and bow waves. All right. Conceptually, they both are the same thing. Why is this not moving for me? There we go. Conceptually, they're both the same thing. The only difference is that bow waves are two-dimensional, shock waves are three-dimensional. All right. So water waves, for example, occur on the surface of the water. And the surface of the water is, more or less a flat surface. So you get sort of rings on the surface of the water, two-dimensional circles. Whereas sound waves create spheres, right? If I'm, talking, you can hear me in front of me, behind me, to my left, to my right, or if you were somehow hovering above me or, below me, you'd be able to hear the sound that way, okay? So that's the only difference between shock waves and bow waves, all right? And because we can't draw in 3 dimensions yet, everything I'm going to draw here is going to be bow waves, but we'll be talking about both, all right? So what happens if the source is moving exactly as fast as the wave that it creates, all right? So let me show you. Here is the answer to that question. All right. So over here in red, we've got our source. He's hanging out. And if I press play, let me move this thing out of the way. Why does this keep popping up? I have not a lot of luck with doing this the way I wanted to today. So if I hit play, what's going to happen is my source right here is going to start moving this way. And watch what happens. See that what's happening is as the wave spreads out, he kind of keeps up with it, doesn't he? All right. And you'll notice that there's this point here, sort of right under his head, where all of the waves he's created have overlapped. All right. What's happening is all of those waves interfere with each other, and you get constructive interference, right? Because you've got a wave plus a wave plus a wave, and it creates sort of a super wave, right? And so if you've ever been in a boat, you know that when you speed up, like if you're just floating at rest, and then, the person driving it suddenly speeds up, the front of the boat goes up, right? So that you get this like, right? And we're having fun because we're in a boat, right? Hooray, right? The reason that happens is because all of those waves pile up and the boat sort of has to go over those waves, all right? It's literally the boat is catching up to the waves that it's produced, and it has to go over them, and it pushes the front of the boat up, all right? In the case of a jet, this would be a sound wave, all right? So what would be happening now is the pilot would be creating sound waves, but he would be catching up to the sound waves that he's creating. And at this moment, the pilot hears what's called a sonic boom, all right? But that's just when the pilot hears it, all right? And it's a result of the fact that he's hearing all of these sounds simultaneously, and he hears what's called a sonic boom. It sounds like a thunderclap. It's sort of him catching up to all the sounds that he's produced simultaneously. Okay? So that's what it looks like if the source is moving exactly at the same speed as the wave that it creates. So now the next question is, what happens if the source is moving faster than the waves? The source is moving faster than the waves, right? Remember here, this drawing that you're looking at here is the source moving at the same speed of the sound of the waves that it's producing, all right? So what happens if it goes faster? And that brings us to our last one of these little video clips. Oh, let's get rid of this. So now look what's happening. As the source creates its waves, it stays in front of it, right? And so what happens is, look, half a second ago, our source here created this little wave right here. But because he's going faster than it, he's ahead of it, right? And so the other thing that's worth noting is that the waves overlap here and here and here and here and here. Each of these rings represents a crest or a compression of a wave. And so every time they overlap, you get constructive interference. All right? So imagine a boat moving. If you imagine a boat moving, behind the boat, you've got this sort of triangular shape that stretches out behind the boat that's often called a wake, right? All right? The sciencey term for that is a bow wave. All right, and it's caused by these water waves all overlapping. All right, if this was a sound wave instead of a water wave, you'd have these sound waves overlapping. You'd have constructive interference there where the waves are overlapping, and so you get super loud sound, and it creates what's called a sonic boom. Okay, so if instead of this being a person, if this was a little jet, gonna make sound effect or it doesn't work. So here's our jet moving through space. All right, and here's the ground down here. All right, and you're standing on the ground looking at the jet going, oh, cool, there's a jet going really fast. What's going to happen is as the jet moves, let me see if I can, if the video will play that long. Oh, dang, it didn't go that long. But so what happens is as the jet, no, abort. As the jet moves, it kind of drags this triangle behind it, this shock wave behind it, and eventually the jet will get to up here, and so the shock wave will do this, and when that shock wave hits the observer down here on the ground, that's when the observer hears the sonic boom. Okay? So there's this misconception that the sonic boom only occurs at the instant the jet breaks the speed of sound, the instant the jet goes faster than sound. And that's true for the pilot, but for anybody outside of the jet, they hear the sonic boom when that shock wave hits them. Okay? So, to add on to this drawing a little bit, so here's what the drawing would look like if your source is moving a little bit faster than the wave. Okay, and you can see the source is just a teeny bit ahead of that last wave that it made. But as the source speeds up, as it goes faster and faster, what's going to happen is this bow wave or shock wave is going to get narrower and narrower. Okay, so in the next one, now the jet's going a little bit faster, or the boat's going a little bit faster. And look, the cone or the bow wave or shock wave gets narrower. And if it goes faster, it gets even narrower. Okay, so that is worth noting that, and I don't think I wrote this in the video, you should write it down, that as the source goes faster and faster, the angle of that bow wave or shock wave gets narrower and narrower. Okay? All right. So I think I already wrote this, but if the object is a boat or some sort of object that's making water waves on the surface, it creates a bow wave, which is called a wake. And then if you're talking about a jet or some other object that's creating sound waves, but remember, it's got to be going faster than the sound wave it's producing, right? It's got to be moving faster than like 340 meters a second. It's over like 700 miles an hour. I just said like a whole bunch. So if the object is a jet, the interference between those waves is going to create a shock wave, because remember, it's three-dimensional now, and we call it a sonic boom. All right, the observer doesn't hear the sonic boom at the instant the jet breaks the speed of sound, but instead at the moment the shock wave reaches him. All right, so I think that might be it. That is it. All right, so we'll watch a video in class about Chuck Yeager, who is the first human that went faster than the speed of sound, and it'll give you a little bit of a kind of a visual behind this. Okay. And I think I'm going to edit in one other video here that gives you another way to look at this. So hopefully I've edited that on here. All right. So there you go.
We're all used to the idea that light travels faster than sound. Think about thunderstorms. You always see the lightning before you hear the thunder, despite the fact that they both occur at the same time. Sound travels at approximately 330 meters per second, which is pretty fast. However, man has been able to beat this speed and break the sound barrier with supersonic travel. The incredible thing about breaking the sound barrier is that it not only produces an audible effect, but also a visible one. Take a look at this picture. You can actually see the effect on the air as the plane blasts through the sound barrier. Isn't that amazing? The reason why this occurs is because as the plane travels through the air, it pushes the air out of the way, which creates pressure waves that travel at the speed of sound. This is similar to the waves created by the bow and stern of a boat as it moves through the water. As the plane approaches the sound barrier, the air cannot get out of the way quick enough, and it is squashed together into one big shock wave that is travelling at the speed of sound. This shock wave begins at the nose of the plane and ends at the tail in steady flight. It forms a kind of cone shape that surrounds the plane, as can be seen here. The pressure inside the cone is not that much greater than normal air pressure. However, since this overpressure is released very quickly, it is audible as a sonic boom. Have a listen to one. There are actually two booms that are produced, one at the nose and one at the tail, which you can see in this video. However, they usually pass over observers almost at the same time, and so most people will only hear one. It's not just fighter jets that can produce a sonic boom. Perhaps the most famous form of transport that could break the sound barrier was Concorde, which was a commercial airliner before it was put out of use in 2003. Space shuttles can also break the sound barrier, but only when they re-enter the Earth's atmosphere. Well, that's all we have time for, except for this last fact. Humans are actually able to produce a sonic boom using their hands. The crack of a bullwhip is actually a sonic boom. This is because the end of it is travelling faster than the speed of sound. Now that's fun. Well, that's all for today. Until next time, remember, science is fun.